Hi, in this video, we will discuss the geometry of vectors. We begin by considering the Cartesian plane with the familiar x and y axes. A vector is a directed line segment that corresponds to a displacement from one point, say A, to another point B. So we may consider this one. We may consider this illustration. So notice that from point A, there is a displacement, and it goes to point B. The vector from A to B is denoted by this symbol. The point A is called the initial point or the tail, whereas the point B is called its terminal point or head. Oftentimes, a vector is simply denoted by a single bold-faced lowercase letter, such as this one, letter V. However, it is difficult for us to write it in a piece of paper, so we usually use this one if we are writing the vector in a piece of paper. So basically, that is just a letter, say V, and an arrow pointing to the right, written on top of the letter. So a vector with its tail at the origin is said to be in standard position. Now, in a Cartesian coordinate system, specifically this one, we have x and y axes. When we try to locate the position of a point, we usually use an ordered pair. For example, we have the ordered pair 3, 2. So if we will try to locate this one in a Cartesian coordinate system, basically the first component, this is the x component, whereas the second component, this is the y component. Now, if we will try to locate that one in the Cartesian coordinate system, so we count 3 units to the right from the origin, of course, and 2 units upward from there. So that coordinate is located here. Now, if we will try to translate this one into a vector, so all we need to do is to draw an arrow. The tail should be on the origin, going towards that coordinate. Then we draw an arrowhead on this portion here, exactly at 3, 2. Now this one, if we will try to name this one using vector notation, instead of writing a parenthesis, we will write a square bracket. Then we proceed with identifying the numbers, the first and the second component. So 3, 2. Now this one is a vector where represented by this one. And this is the ordered pair. Now, we call this one as a position vector. Why? Because it tells us a position. The vector tells us a position relative to the origin. Most of the time, when we perform operations, we prefer to use column vectors instead of row vectors. So this one, this is a row vector. This can be represented using a column vector using this one. Notice that the first component of the row vector is on top of the second component of the row vector in its equivalent column vector. So take note that the order of the component is important when we talk about vectors. Similar to ordered pairs, remember that 3, 2 is not equal to 2, 3. That concept can also be applied in vectors. Therefore, 3, 2, this is a row vector, is not equal to 2, 3. So always remember that the order of the components is important. Earlier, we defined vector as a directed line segment that corresponds to a displacement from one point to another. Suppose we have an object and that object was displayed twice. How do we mathematically represent that displacement? That displacement now will be represented by vector addition. And in this portion, I will try to geometrically represent vector addition, and I will also demonstrate how to perform the operation numerically. Before we can geometrically represent the vector addition, we need to define first the head to tail rule. So given vectors u and v in R2, translate v so that its tail coincides with the head of u. The sum u plus v of u and v is the vector from the tail of u to the head of v. Later, I will try to demonstrate that definition. We have here a remarks. The set of all vectors with two components is denoted by R2, where R denotes the set of real numbers from which the components of vectors in R2 are chosen. So if we have three components, we will represent that one with R3. So this is three components. And if we have four components, that will be represented by R4, and so on. Now to illustrate vector addition geometrically, let's have the first example, example 1.1. Suppose we have two vectors, vector u, which is the first displacement, and that is equal to 3, negative 1. And we have another vector v, which is the second displacement, and is equal to 1, 4. Let's try to compute and draw u plus v in a Cartesian coordinate system. So let's perform first numerically the operation. To perform vector addition, it is advised to convert the row vector into its equivalent column vector. So the equivalent column vector of u is 3, negative 1, whereas the equivalent column vector of v is 1, 4. To perform the operation, that's addition, we will just add the corresponding components, which means we will add the first components of the two vectors, and we will also add the second components of the two vectors. That is 3 plus 1 and 4 plus negative 1. Performing the operation, we get the new vector, which is equal to 4 and 3. To represent this one geometrically, we will try to draw first the vector u. So to do that, we need to count 3 units to the right and 1 unit downward because it's negative. So that's 1, 2, 3, and 1 unit downward. So vector u is somewhere here. Let's try to draw a vector whose tail, or which tail is at the origin. And let's try to specify the arrowhead. So ayan. That's vector u. Now to perform vector addition geometrically, instead of starting from the origin to draw vector v, we will now start at the tip of vector u. So to do that, we will count 1 units to the right, or 1 unit to the right, and 4 units upward. 1, 2, 3, 4. So it's somewhere here. And with that, we will try to create a vector from point A, or from the tip of the, or from the head of u to that point. So if we will try to draw now the new vector, this is color blue, and that vector now is equivalent to 4, 3. So that is how we do it geometrically. Now, let's consider example 1.2. The problem with 1.2 is that this is a vector with 3 components. Therefore, to illustrate this one geometrically, we need to have the x, the y, and the z column. So we need a 3-dimensional space to illustrate this one geometrically. And to illustrate a 3-dimensional space in a 2-dimensional screen, it is very difficult to do so. Therefore, we will try to, do it numerically instead of geometrically. So to perform the operation, all we need to do is to convert the row vector to its equivalent column vector. So vector u will be equal to 2, 1, 3, whereas the vector v, the column vector for v is negative 2, 2, 5. And to perform the operation, we will add the corresponding components. So we will add the first components of the two vectors, the second components, and the third components. And that is equivalent to 2 plus 2, 1 plus 2, and 3 plus 5. Performing all the operations, that is equal to 4, 3, 8. So this is now the new vector. The next operation is scalar multiplication. We define the operation as, given a vector v and a real number c, the scalar multiple c times the vector v is the vector obtained by multiplying each component of v by c. In general, we have this solution. Geometrically speaking, c times vector v is a scaled version of v. So we will try to do this one numerically and geometrically. Now, let's consider example 1.3. Suppose we have a vector v whose components are negative 2 and 4. We are asked to compute and draw 2 times v, 1/2 times v, and negative 2 times v. And let's see what will happen into our original vector. Let's consider the first example, example 1.3. Suppose we are given a vector v, which is equal to negative 2, 4. We are asked to compute and draw 2 times v, 1/2 times v, and negative 2 times v. So we will do this one geometrically and numerically. But first, let's do it numerically. So let's start with 2v. So we have 2 and the vector v. So I will use this symbol instead. So this is equal to 2 times the column vector negative 2, 4. So I converted the row vector v into its column vector. To perform the operation, so we will multiply each component by 2. That is, we have 2 times negative 2, and we have 2 times 4. Performing the operation, we will have the result. And that is equivalent to negative 4, 8. If we will try to do this one geometrically, let's try to illustrate first the vector v, negative 2, 4. and that is -2, 4. It's somewhere here. Let's use another color. This one. And we start from the origin, from here, and draw arrowhead. So this is vector v. Now, the new vector, which is -4, 8, we will try to illustrate that one. So -4, 8 is somewhere here. We will try to use another color. So that is this one. From the origin to this point here, and draw an arrowhead. So notice that the vector was scaled up, and this was scaled by a factor of 2 actually. Now if we will try to perform the next operation, that is 1/2 times v, so that is 1/2 times v, that is equivalent to 1/2 times the vector -2, 4. So we will multiply each component by 1/2. That is 1/2, and we have 1/2 here. So the first component is -2, and the second component is 4. So we perform the operation, that is -1, 2. And if we will try to illustrate this one in a Cartesian coordinate system, so that is -1, 2. So this is here, and this is the new vector. Let's try to make it a little bit cleaner. Okay, that's acceptable. Okay, and notice that the vector now was reduced into half. So the original vector v, was scaled by a factor of 1/2. And finally, let's perform the operation -2 times the vector v. So this is equivalent to -2 times the column vector. Perform the operation. So we will multiply each component by -2. So we have -2 and -2. This is -2. That's the first component. And this is the second component. Perform the operation. So we will have our answer. That is +4 and -8. And to illustrate the new vector in the Cartesian coordinate system, that is somewhere here. And let's try to draw the vector. Start from the origin. This is the origin. And let's draw an arrowhead. So notice that the original vector v, was scaled by a factor of 2, and it was inverted because we have a negative sign in our scalar multiple. Now let's perform the second example. Let's try to perform 2v, 1/2 times v, and -2 times v using this vector v, which is equal to -6, 8, and 2. So we start with the first one, this one. So this is equivalent to 2 times, so from the row vector, we will convert it into a column vector, 2. And let's perform the operation. So basically, we will multiply each component by 2. So I will not write it anymore. So 2 times -6 is -12. 2 times 8, that is 16. 2 times 2 is 4. So we now have the new vector. Next, we have 1/2 vector v. And that is equal to 1/2. And the column vector is -6, 8, 2. So we will multiply each component by 1/2. So this is equivalent to -3. 1/2 times 8 is 4, and 1/2 times 2 is 1. So this is now the new vector. And finally, let's perform the last operation. So we have -2. The column vector is -6, 8, and 2. And this is equivalent to +12, -16, and -4. So that's how we perform, or that's how we do scalar multiplication.